Hey there guys, it's me again. This is going to be topic 5, bonding overview. For this one I'm going to just read the front page a little bit and kind of talk about each of the things. I hope you can see me. And yeah, we're going to talk about basic characteristics, ionic lattice energies, covalent Lewis dot diagrams, and intermolecular forces. Alright, so the first thing we're going to talk about are the 3 types of intramolecular forces. So ionic, covalent, metallic. Covalent bonds are made of 2 nonmetals. They share electrons, so think like sharing is caring. You guys should know that by now. Polar covalent bonds have unevenly shared electrons. Nonpolar bonds have, nonpolar covalent bonds, have evenly shared electrons. So having polar and nonpolar bonds is not the same thing as having polar and nonpolar molecules. The bond is strictly based on electronegativity. So if you think of the compound HF, to decide is the bond polar or not, you would look at their electronegativities. If they're different, they have different electronegativities, they're polar. So you would just say they're sharing unevenly. Covalent compounds are called molecules, so if they ask for something with molecular bonding, they're talking about covalent. They have low melting points, they're soft, they do not conduct. Ionic compounds are metals and nonmetals. These transfer electrons to form ions. They conduct electricity only when dissolved, and they have high melting points and are very hard. Metallic bonding is when you have one type of metal. So like I have a sheet of aluminum foil, so you have a lot of aluminum. Electrons are moving. There's always conductivity as a result of the moving electrons. Okay, so now that we know those bonds, in those bonds you can have single, double, or triple bonds. Carbon is a good example because it makes it can do any of those kind of bonds. So single bonds are long, they're weak, they're considered to be sigma bonds, which are head-on bonding, and they have a bond order of 1. A double bond is kind of in the middle, slightly shorter than a double or than a single, but longer than a triple. They contain head-on and sideways bonding. So head-on bonding is your sigma, so they have 1 sigma bond, and then they have sideways bonding, which is called a pi bond. Their bond order is 2. Triple bonds are the shortest and the strongest. They have head-on and sideways bonding again, so their head-on is sigma, and the sideways is pi. So they have 1 sigma, 2 pi. The bond order is 3. Alright, so I'm going to show you a compound, butene, and we're just going to count up how many sigma and pi bonds they have. Okay, so each single bond is a sigma. So single is sigma, double is 1 sigma, 1 pi, triple 1 sigma, 2 pi. So let's do the double first. So right here you have 1 sigma, 1 pi. And so let's just count the rest of the sigmas. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So you have 11 sigma bonds, 1 pi bond. Let's also take a look at hybridization. We're going to talk about that later. But basically, if you're given a compound, especially with carbons, you want to look at each carbon individually and see how many attachments you have. 1, 2, 3. So sp2, 1s plus 2 p's equals 3. 1, 2, 3, sp2, 1, 2, 3, 4, sp3, 1s, 3 p's equals 4. On this one, 1, 2, 3, 4, sp3. We'll talk about that in a minute. Okay, ionic compounds and lattice energy. So ionic bonds are held together by a really strong electrostatic attraction between its ions. Coulomb's law says that the more highly charged ions form stronger bonds, and less highly charged ions are weaker. If the charges are the same, smaller ions will form stronger bonds. This affects your melting and boiling point, because as you have a stronger ionic bond, the forces between your ions means they're stronger, and so boiling or melting becomes higher. So lattice energy is equal to Q1, Q2 over, I think, D, where Q1 and Q2 are your charges, D is your distance, or your size, you can think of. So if you're looking at like NaF versus CaO, +1, -1, +2, -2, this would have a greater Q value, so it would have a stronger bond. More energy is needed to break it apart. If they're the same kind of bonds, look at size, or same kind of charges, look at size, and then you can decide from there. Okay, moving on. We have covalent shapes and derivatives. Okay, so if you have 2 bonding sites, 0 non-bonding sites, you are linear. Hybridization, so 2 total is an SP. Your angle is 180, and as long as your attachments are all the same, you are nonpolar. Okay. 3, 0. These tend to have group 13 central atoms. This is trigonal planar. 2, 1 comes from trigonal planar overall geometry, and it is bent. Okay, these add up to 3, so SP2. 1, 2, 3. Okay, angle for trigonal planar is 120 degrees. It looks like this. For bent, it's less than 120. So if you consider something that's bent, like SO2. Okay. This lone pair of electrons needs room to move, like to spread out so they don't repel each other. So as they spread out, it makes these bonds squish together. So that's why your angle is less than 120. If you're just a strictly 3-0, you're nonpolar. If you're a 2-1, you're always polar. Okay, 4-0 is a tetrahedral. And these are always SP3. Okay, tetrahedrals have angles of 109.5, and they're going to be nonpolar as long as their attachments are the same. A 3-1 is a trigonal pyramidal. That's like NH3. So NH3, again, has your lone pair of electrons unbonded, so they squish the angle, so your angle's less than 109.5. And they are polar. 2-2 is bent, so this is your water example, or H2S. Same thing, 2 non-bonding electrons squishes your angle, so it's going to be less than 109.5. It's going to be even less than NH3, and polar. Okay, 5-0, trigonal bipyramidal. SP3D. And sometimes the AP exam puts that D in front. Don't worry about that. It's the same thing. So this is what that kind of shape looks like. You have PCl5. Cl, 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 Cl. Okay, so these are in the axial position, equatorial. These on the equatorial plane make like a trigonal planar, so the angle here is 120. In the axial plane, we make a 90-degree angle. So 120, 90. A 5-0 is nonpolar. 4-1, seesaw. So you just get rid of one of your equatorials. 3-2, T-shaped. And this is linear. Alright, so seesaw, less than 120, less than 90. T-shaped, less than 120, less than 90. Linear, 180. So polar, polar, like XEF2 would be nonpolar. Okay, 6-0, we have octahedral. Okay, so that's SP3D2. So again, sometimes they put this D in front. This one looks like SF6. So we have F, F, so it's kind of hard to tell with just a drawing. That's why a three-dimensional model is better. But this has like a square here in the center that's flat, and then you have two poking up and down. So it's kind of like that. Okay, so the angle between all of these is 90 degrees. And that one's nonpolar. Okay, 5-1 is square, pyramidal. So take off the bottom maybe or the top. Angle less than 90, because now that you have lone pairs, it's going to squish them. Polar. Square, planar. You'll have less than 90, and you can say this one's nonpolar, like XEF4, something like that. Okay, hybridization, so that all this SP business accounts for the molecular geometries we see. So sometimes, so bonding has to occur when you have unpaired electrons. Sometimes it doesn't look like you'll have unpaired electrons according to your electron configurations or orbital diagrams. So to account for the shapes we know exist, we talk about this theory of hybridization, which mixes orbitals to create equivalent bonds. So if you think about CH4 methane, sp3, there's a mixture of 1s and 3p orbitals. And so each of these bonds is now called an sp3, and they're the same size. Polar versus nonpolar molecules, this is based on symmetry. So polar molecules have an asymmetric, and this is key, distribution of charge. So you can't just go ahead and say, oh, you can't cut it in half, or yeah, you can't cut it in half. That's not going to work. You need to say your charge distribution is uneven, something like that. So the way we do that is we draw our picture, we see if it's symmetric, if it's not, it's polar. I remember I said Alaskan polar bears like water, asymmetric, polar, water. Remember it. Okay, nonpolar molecules have a symmetric distribution of charge. So their dipole moments, which is just when you have a positive and negative end, they cancel each other out. So 0 dipole moments, all dipole cancel, it is nonpolar. So symmetric distribution of charge, also called 0 dipole moment. A good example of that is C6H6. Oh, this is a good example for the next one also. Okay, so C6H6, they'll sometimes use this as benzene. These are H's around. All their dipole moments cancel. They have a 0 dipole. So a couple exceptions to the octet rule. Molecules that are okay being electron deficient can have these 3 different central atoms. So if you have B doesn't mind having just 4 electrons. So you could, oh no, that's a lie. Be only likes 4. So you could have BeH2 with 4 electrons. B and Al enjoy having 6. So these are your trigonal planars. Okay, expanded octet, any element in periods 3 through 7 have d orbitals available, which allows them to have extra electrons on the central atom. So that's something like SF6. So because S has d electrons available, not that they are used currently, that can be where the extra electrons go. All right, so last thing, resonance structure, and I drew this one up here, so we'll just take a peek. Resonance structure is when you can have double bonds that can switch places. So this is one form of the structure. Another one would be with your double bonds there and your singles where your doubles are currently. Resonance structures have all the same type of bonds because you don't really consider this as being 3 singles and 3 doubles. You consider it as a 1 and 1/6 bond. A 1 and 1/6 bond is longer than a double, shorter than single. That also means they're stronger than a single, weaker than a double. All right, and then SO3. So I'm just going to draw this one out. Okay, so S has 6, O has 6 valence electrons, so I'm allowed to have 24 total. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, and then I know that there's going to be a double bond up here, 24. So this double bond could be next to that O, or it could be next to this O. So because it has 3 places to switch spots, it's a 1 and 1/3 bond. So sometimes they'll say like, what is the reason why all of these bonds are equivalent, something like that. All right, the end of, oh no, not the end, almost done. Hang tight. Okay, we have formal charge. This I don't really think is super important. Formal charge lets you know the appropriate electron configuration. You take the valence electrons and subtract 1/2 of the bonding electrons plus the non-bonding electrons. So for example, if we have CH3Cl, I like to just write them in order. CHCl, all these H's are going to be the same, so you just need to write 1. Alright, so valence electrons. So valence electrons from C, 4, each H, 1, Cl, 7. Okay, you're going to take 1/2 the bonding electrons and then any non-bonding electrons. So take a peek at C. You have 2, 4, 6, 8 bonding electrons. Half of that is 4. Subtract that, you get a formal charge on carbon of 0. H, you have 2, take half of it, 1, 0. Okay, Cl is 7, so you have 2, take half of it, 1, 2, 3, 4, 5, 6, 7. Oh, look at that, I drew it right. Okay, formal charges closest to 0 are best. Okay. Last thing, intermolecular forces responsible for things like phases of matter and boiling point. So if they ask a question like, why is I2 a solid and F2 is a gas? It's because of their intermolecular forces. Draw molecules to figure out polarity. This will be helpful. Okay, so the 3 main types that we have talked about, hydrogen bonding, hydrogen attracting to an F, O, or N atom on another molecule. So something with really, really strong electronegativities. Hydrogen bonding is your strongest force. When you have hydrogen bonding, your boiling point increases as your electronegativity increases. So I'm pretty certain that NH3 has the lowest. Between HF and H2O, H2O will have the highest boiling point, even though O is less electronegative, and it's because there are 2. Okay, so next one, so we have dipole-dipole. These are between polar molecules. Boiling point increases as size decreases. So that's kind of like the ones we've been talking about, like same thing with ionic. As you decrease the size, the strength increases. So for these, as size increases, strength decreases. London forces is opposite. London forces are caused by induced dipoles. So basically, if you have an atom, your negatives are normally evenly distributed. At some point, the electrons are moving, and you might end up with the electrons on the same side. This would be a delta negative or a partial negative charge. This would cause the atom next to it to shift its electrons away because it wants to be attracted to this positive, which would cause another one to do that. This is called the polarizability. So this little force here is your London force. So all molecules have London forces, but for nonpolar molecules, this is the only type of force they have. So if you have like H2O, H2O can have hydrogen bonding, dipole-dipole, and London. But if you have H2, only London. Boiling point increases as size increases. Larger atoms, so you could count up the electrons, are more polarizable, which just means your dipole can be induced more easily. Alright, now we're done for real. Bye-bye.